Hello everyone and welcome. My name is Branko and I'm a creative roads manager here at MikroC company. Thank you for joining today's webinar session. In the next 30 minutes, we are going to explore how embedded development has evolved from the traditional library-based approach in MikroC development environment to a modern NECTO-based SDK-based development model from within the NECTO Studio IDE. You will get hands-on examples, you will see real-world code comparisons and understand why and how NECTO enables faster, modular, and reusable embedded development across multiple microcontroller architectures. Right, so let's start. Let's zoom out for a moment and ask a broader question. Why do modern embedded developers need to think beyond just blinking an LED? Because we do not longer live in a world where embedded development is tied to a single microcontroller, to a single toolchain, nor a single vendor. In a library-based workflow, like in MikroC development environment, you write highly specific code tied directly to the underlying registers of one particular microcontroller. That code works beautifully until it doesn't. As soon as requirements change, for example, whether to do performance limitations or cost constraints or new hardware availability, or perhaps customer switching platforms, or simply wanting to scale the same solution across different product lines, you realize you are locked in and you are stuck rewriting everything from scratch for a new architecture. That's where SDK-based development in NECTO makes the difference. Instead of programming registers, you work with drivers. You are no longer just writing code for one device. You are building scalable embedded solutions that can be reused and extended. And that's what today's webinar is all about. Shifting your mindset from device-level coding to platform-level engineering, or should I say, from single-use static code bases to portable multi-architecture workflow. Let me now show you how this approach looks in practice and how MikroSDK turns one blinking example into a universal reusable application that works across architectures. Alright, let's imagine we want to toggle LEDs, like this one over here, to various ports on a PIC microcontroller, like this one over here, right? Here is the MikroC Pro for PIC code. Here it is over there, on the left-hand side of the NECTO Studio IDE. Alright, let's slow down and walk through this example together. We are now looking at a typical GPIO control snippet written in MikroC Pro for PIC IDE, but I opened this exact code in NECTO because NECTO can open this kind of project. This is a bare metal register level approach that many embedded engineers are familiar with. Let's go line by line. Okay, this is your main entry point, int main void. The function that gets called when your microcontroller boots up. Nothing unusual here. It's where all the magic starts in embedded applications. Okay, next, now, this code over here. Here's what this block is doing. We are configuring the data direction for each port, A, B, C, D, and E. In PIC microcontrollers, the trace registers that determine whether a pin is set as an input or output. Trace A is equal to 0 means all bits or all pins on a port A are set to output. So trace A is equal to 0. Same goes for ports B, C, D, and E. And why are we doing this? Because we want to control the state of those pins, turn them high or low, which you can only do if there are outputs. So right now we have made the entire port bank act like output drivers. Okay. Right, next is the do while loop. This starts our infinite loop. In embedded systems, we often run the main logic inside a loop that never exits, unless there's a hardware reset or power cycle. Let's now look at the LED toggling logic. This logic over here. In this section, we are writing a value of 0x00 to each LUT register. In PIC architecture, LUT is the output latch for port A, B, C, etc., etc. So let A or let B is equal to 0x00 turns off all the bits on port A. In real-world terms, that means all connected LEDs go off. You can also write these as binary for more clarity. So for example, 0B, then 8 zeros. Something like this. 0B, 1, 2, 3, 4, 5, 6, 7, 8. But 0x00 is just fine. It simply means everything is low. Okay, I'm going to remove this one and I'm going to switch to the next section. And the next section is the delay line. We insert a 1 second delay so the LED state is visibly noticeable. If we skipped this delay, the toggling would happen so fast you would barely see anything. The delay millisecond, this functionality over here, this method over here, is provided by the MikroC built-in library. It's a blocking delay, meaning nothing else happens during that time. Now we are writing this line over here. For example, let A is equal to 0xFF, which means all 8 bits of port A go to logic high. So the sequence is off, then delay, then on, and then I'm going to repeat the same code over and over again. And why is that? Because of this line over here. This loop runs forever, toggling LEDs on and off every second. It is a classic blinking example, perfect for verifying your board and connections or learning the basics of GPIO. Okay, some final notes on the MikroC Pro approach. This kind of code is architecture specific. It is designed for PIC microcontrollers. It is hard-coded to use trees and LUT registers, and it is not portable to other MCUs like STM32, AVR or DSPIC. You would need a completely different set of instructions to do the same thing on a non-PIC architecture. And that is the key limitation we are addressing in today's webinar. Because next we will look at the SDK-based version, and you will see how one code base can work across multiple microcontrollers with none of these register level rewrites. Okay, let's now look at how the same LED blinking behavior is implemented using MikroSDK inside NECTO Studio. Just make sure to open the package manager, search the GPIO keyword, and you will find the GPIO demo pack software package. Make sure to install it, and after that make sure to open the complete GPIO demo pack. And after you open it, you will see something like this. Okay, GPIO demo pack, which has digital input output example, which has LED blinking example, which has LED curtain example, and which has port example as well. I'm going to focus on the port demo, which in essence is basically the same thing that we have done but with the bare metal code. Okay, let's close this main file and open this one. Okay, this code may look longer, but do not worry, it is doing something incredibly powerful. It works across multiple architectures without rewriting a register level code. Let's go line by line and unpack what's going on here. Okay, we have a comments, which is nice. After that, we have something like this. We begin with an optional but critical include pre-init header file. This handles low-level MCU initialization, like setting up clocks or peripheral defaults. NECTO Studio inserts this automatically when it's needed for your microcontroller. If you remove it, you might end up with no clock or stuck startup. Now onto the next one, those header files. Let me break this down. Board header provides access to board level definitions, pin mappings, headers, onboard LEDs, etc. etc. Driver port header file, this is the port driver API, a high-level abstraction for configuring and writing to digital ports. This is what we want to mimic. And the last one is the ports header file. It contains an port array of all available ports on the selected microcontroller, fully abstracted from the hardware. These header files, those three, are universal across most supported microcontrollers. You do not need to care whether you're using a PIC or ARM. The SDK takes care of that for you. After that, we have this code snippet. This is the delay handling compatibility. This section conditionally includes the delay header file, depending on the version of the MikroC core. It ensures your code to delay functionality, the delay method, later in the code, works without issues, regardless of compiler version. This code over here is the great example of how the SDK wraps complexity and keeps your code forward compatible. Now, this part over here. Depending on whether your MCU's ports are 8-bit or 16-bit, these macros define port mask, this guy over here, which is a bit mask used to select which bits we want to manipulate. We have a value on and value off, which are logical values to send to the port. So you do not have to guess or hardcode these values for every architecture. The SDK checks this at compile time and adjusts. The next line of code is this one, static port type port. Here we define a driver context structure named port. Think of this as the state of your port, which the SDK uses to manage direction, masking, and value writes. You can reuse this single port variable across many pins and many ports. It is lightweight and memory safe. Next up is this part of the code. Here we enter the main function. Again, NECTO makes sure we insert pre-init early. It configures essential low-level behavior like clock setup and memory initialization. Now, let me pause just like here. We are looping through all available ports one by one. Port number or port num is auto-generated based on your selected microcontroller. Port array gives you a handle to each port. Port init initializes that port for digital output using our shared port context. And port write, this line over here, it sends 0xFF or 0xFFFF to the port, turning on all connected LEDs. This block gives you a ripple effect. Each port lights up in sequence, half a second apart. What's powerful here is you do not care how many ports or your MCU has or what they are called. The SDK handles it for you. Now we are going to loop backwards. Same idea, but now we are looping in reverse. Value of this value over here, it turns off each port one by one. Once again, half a second delay makes the visual transition nice and clear. This line of code gives a clean waveform style LED animation without using any low-level register calls. Right, so what does this simple project tell us? This single project works across multiple architectures. So for example, PIC, ARM, AVR, you name it, which basically means it is cross-architecture compatibility enabled. Let me just transfer to the NECTO Studio right now. Okay, perfect. And now I have already connected to the this development board over here. It has PIC18 F47K42 microcontroller, and here is the code that I'm just going to flash right now. And after the flashing, it will start blinking in the specific SDK-based scenario. So let me transfer to myself right now. Okay, perfect. This is the cross-architecture compatibility. Number two, you didn't have to use the trees a lot or refer to any datasheet. So no waste of your time, which means faster development, especially in multi-product or fast-paced projects. Number three, you use the principle of modular drivers. Specifically, I used modular driver for GPIO, but there are more drivers for you guys. For example, ADC, SPI, UART, I2C, etc., etc. And number four, you wrote one piece of logic, which in essence is cleaner abstraction, so your code isn't tied to any vendor. This is in the essence of the SDK-based embedded development. Modular, portable, and future-proof. You can move fast and prototype smarter without getting stuck in MCU-specific details. Now, I'm going to transfer to the NECTO Studio once again, and I'm just going to show to you guys that this code is definitely going to work on some other microcontroller architecture. And I'm just going to search for for example, STM microcontroller. I'm just going to connect to some development board. Okay, let's say this one. Okay, perfect guys. I'm just going to flash this code right now. And after